Well, hello everybody, and welcome to another week. So what we've got going on today is we have our usual homework due on Wednesday. There will also be our usual quiz on Wednesday, and that quiz on Wednesday will cover applied optimization, so the stuff you had homework due on Sunday on. And then one new thing is, very few people have been using my office hours lately, so I've decided to change them into more of a time where you can just drop in and ask quick questions if you would like. So, and I've also got the TAs to help out with this. So there will now be two kind of study sessions, or you can just drop in and ask questions, or you can come there and work on homework and stuff. There'll be one on Tuesdays from 2 to 3 p.m. And then there will be one on Sundays, 3 to 5 p.m. Okay, and then so basically I've gotten rid of my Tuesday office hours, and they're becoming this. And then my Thursday office hours are still the same time, but I'll send out an announcement with all this information, and it'll have links to the Zoom meeting where you can just pop in or out if you like. Okay, so look for an announcement later today that'll give the details on this about. Maybe that'll be a better use of my office hours. And sort of along that same lines, as maybe I should add here is, use the, if you were using the if you were using the Math and Stats Center before, they're still taking appointments for tutoring. So I encourage you to still go and use that. You can set up one-on-one appointments with a tutor every week, and that's still a useful thing. Okay. So any questions before we get started? I guess one other thing is I believe all your exams are graded for your section. So you can go and look at your exam grades, and you can look at the actual grading on the exam in OneNote. Okay, so let's get back to the math then, if there's no questions. So if you remember, what we were talking about on Friday was antiderivative. So we were asking the question, we spent a long time understanding how we understand rates of change, which were derivatives. Now we're asking, how do we reverse that process? If we know the rate of change, how do we discover what the original quantity was doing? Okay, so we're going to continue that. But now we're going to get into sort of the sort of geometric interpretation of the antiderivative. Like the geometric interpretation of the derivative was the tangent line, but it's much different for the antiderivative. We're going to start simple. So if you remember, right, if you have, let's do it in a different color. So remember, if you have position, in units of distance, then its derivative is velocity, right? And so now we're asking the question, how do we go from velocity back up to position? That's sort of one of the classic examples of sort of this undoing the derivative idea. So if we're just given information about a velocity, how can we decide what the position was? Okay, so as the most simplest of case, let's look at this example. So it says, you have a car, let's suppose it's moving in a straight line, and its velocity is given by this graph. Okay, so these are supposed to be flat lines. These red lines are supposed to be perfectly straight. So this is v of t. So the red part is v of t. And our question is, What is the position function? Maybe before we ask for the position function, let's ask something simpler. What is the position of the car at time 5? And it's going to turn out we can't say exactly what the position is unless we give another piece of information. So this is basically the same idea as what was behind those initial value problems we did. Like when we undo the derivative, right, we get this, that's taking the antiderivative, so we get like the plus c. We don't know what the constant is. And one way to figure out what the constant is to give a point on the graph. And so the point on the graph here is we're going to assume, let's write that down here, assuming that it started at position 0. So that would be saying S of 0 is 0. So initial, or the place it started, we assume that's time 0, and we assume that the position is also 0. Okay. And then let's ask the same question for what about time 10 hours instead of 5. Okay, so the basic idea here is, for the first question, we're asking at what happens at time 5. So we know the car started at some position 0, and then what does the graph say happened between 0 to 5? So 0 to 5 is in here, and it said basically that the velocity here was a constant 10, right? Because it's a constant there. And so if you have a car that's going 10 miles per hour for 5 hours, you would expect the answer to be something like I wrote this kind of awkwardly. Let's move this down. So what we would, whoops. So what we would think our answer would be just position at time 5 hours would just be 10 miles an hour times how long they did that for, 5 hours, to be 50 miles. Or the mathematical way of saying that is S of 5 we would think would be 50. Right, so not too bad when the function's constant, right? Now, if you ask the same question for 10 hours, so we know what happened between 0 and 5. Now, what happened between 5 and 10? So 5 and 10's over here. During that time, the car had a velocity, let's assume that it was a constant 20 from the graph. And so we know by the time 5 hours had passed, they had gone 50 miles. So between the 5 hours and the 10 hours, that's another 5 hours passing of going 20 miles an hour. So now we would expect that at t equals 10 hours, so S of 10 should be 20 times 5, 20 times 5. So they went 100 miles plus the original 50 miles they went. So that would be 150 miles. Right, so all we said is that during the first 5 hours, they went 50 miles, and in the second 5 hours, they went 100 miles. So in total, they went 150 miles, right? Okay, so this is not anything super amazing, right? But the point of this exercise is to notice that these numbers we got, the 50 and 150, we can phrase them in a geometric way. So like looking at the graph. So if I look at this area, this has area 50, that rectangle, right? Because it has height 5 and width 10. If I look at this other rectangle, this has area, 100. 20 times 5 is 100. Yeah, and then so what we found here is that so one way of phrasing this is that the net change in position, so how far they traveled, like where they ended up versus where they started, well, that one way of calculating that, at least in this case, and it turns out to always be that way, is the area between the velocity function and the horizontal axis. Okay, so the basic idea here that I wanted to emphasize is when we're doing antiderivatives, instead of having a thing like a slope that we can look at on the graph, instead we have to look at areas. People say area under the curve, but what they really mean is the area between your function and the x-axis, the horizontal axis. Okay, so that's going to be the main idea for today, is that if we want to find a change in an original function given a rate of change, we want to calculate some sort of area. Okay. So for example, so maybe let's just do another example real quick. This one we'll do a little quicker. So let's say we have a graph that looks like this. So this will be a velocity graph. So this is another example. Let me throw some numbers in here. Let's see. We'll have let's move it down here. Let's have a 2 up here, and like this, so this down here will be -3. Okay. So we can imagine that this is again the velocity of a car. And let me give you 2 additional values. We'll call this place 8 and this place 10. 10 should probably not be that far out. Okay, and this axis will be in hours, will be our time axis, and this will be in miles per hour. And we want to ask the same question again. And now wouldn't be so obvious, right? Because at every moment in time, their velocity is changing, right? It's going from -3 miles per hour. So maybe this isn't a car. Maybe this is like a runner or something. They're going from -3 miles an hour. Then at 8 they go up to, they're stopped. They're going 0 miles per hour, and then they keep going up, right? So their velocity is changing. So it might not be clear how far they went. But So what is the displacement over 0 to 10? Okay, so there's this kind of word displacement that gets thrown around. Displacement is always just the difference of two values. It's how far something changed or how much something changed. So how, like, here the displacement would be what was its position at 10 minus wherever it started. We're not given where it started, so that might be a little confusing, but we actually don't need it. So displacement will be like how far something ended up versus where it started. And so we're going to ask, what's the displacement? Maybe a better way to say it at this point is between t equals 0 and t equals 10. And the answer is going to be just like before, and this may not be obvious, but that's what we're going to spend the rest of today talking about is it's always going to be given by area between the horizontal axis and the graph. Okay. So to figure out this, we want to figure out between 0 and 10 would be kind of this region, right? And we want to figure out what's the area between our graph and the horizontal axis. So that would be this area. So we're going to try to calculate that area, and that will give us our answer. And I'll try to explain why in a little bit. And these are just triangles, right? So this one would have, let's see, it would be 1/2 the base times the height. So the base is 8, and the height is -3. And so maybe here's an important point that we haven't mentioned yet. Whenever we talk about area in this section, we really mean signed area. And so we'll talk about this more, but signed means if it's under the x-axis, if it's under the horizontal axis, this counts as negative area, which is why we have to say signed area, because area is usually a positive number. So this comes out to be a positive number, right? And we're really thinking of the height as being -3. And then this one has 1/2 times a width of 2 times a height of 2. So the total answer would be what? It would be S of 10. So the displacement, how far it went overall during this interval, would be -3/4 from the first one plus 2. So they will, wait, no, that was totally wrong. This should be -12 plus 2, so that would be -10 miles. So this means that the object, whatever it was, went backwards 10 miles from where it started. So after 10 hours, it went backwards 10 miles. Okay, so this is going to be our general idea. You probably don't understand everything yet, which is okay. But whenever we're trying to find a displacement or a change in the original function, which is related to antiderivatives, we're going to be computing areas under the curve, or areas between the function and the x-axis. So that's our goal for the rest of today. So that's our goal for the rest of today is to understand how to areas between functions and the horizontal axis. And here we have to remember that we're really talking about signed area. So if something's underneath the x-axis, we're going to call it negative. And people, instead of writing this whole long thing, people often just say area under the curve, where the curve's the function, or the area under the function. Okay. Okay, so let me give you an idea of how this works in general. Okay, so let's suppose we have some function. Let's not make it too complicated. Just, whoops, that's way too big. Okay, something like this. And maybe I choose an interval. So let's have an interval from A to say B. And say I want to calculate the area under f of x in the horizontal axis. So we would be asking, what's this area? Now that's not like a nice shape, right? Because the top is this curvy thing. So it's not like a natural shape where we have a formula for it. And so the idea is, so I'm going to have to erase this so I can draw the picture, but that was the area we were talking about. And the answer is we don't really know how to find formulas for these yet. Later we will. But what we're going to do is we're going to imagine that we chop up the interval into a bunch of little pieces. And on each piece, so say on this first, let's say on this first little piece, what you would do is you take, so you kind of have this little piece of the graph here. And even that, if we were just wanted to know what that area is, it's still not a nice shape because the top of it is still curved, right? And so what you can do is you can instead make your life a little simpler, and you can just make the top of it flat by just imagining that the function was just constant at the same value as it was at the right side. And so if you do this on all the intervals, you're kind of just replacing the function with this bunch of little constant functions. Maybe I shouldn't have drawn so many of these. And we now know what the area of each of these is, right? Each of these is just a rectangle. And so if you calculate all the areas of these rectangles, it gives you, an approximation. Okay. And of course, it's going to be a little off, but the idea is going to be that, the more rectangles or the more times you divide the interval, the more accurate you get. Okay, and so the way this is going to work is we're going to figure out how to estimate things using rectangles like this. And then we're going to ask, what happens if we make the number of rectangles really, really huge? And that will be a limit at infinity when we make something really large and see what happens to it. Then it'll approach the exact area. So it's sort of like the reverse process of derivatives, right? Derivatives, we ask, what happened when something went to 0? And we got the derivative. Now we're sending things off to infinity to get the antiderivative. Okay, and so I have a little demonstration that might help. Okay, so here we have the function 2 sine times 2x. And suppose you wanted to know what the area between 2 sine of 2x and the horizontal x-axis was, between 0 and 4, right? Between these blue dotted lines. It's hard because I can't point at things in the graph, can I? Yeah, I don't think you guys can see my mouse. No. Well, what you could do is you could divide it into a certain number of rectangles like this. Here they're showing them where there's 4 rectangles, and over each of the little intervals you chose the right side. And the point is, as you divide it into more and more rectangles, like if you divide it into more pieces, you get more rectangles. And the idea is if you make the number of rectangles really large, the area is basically the same as the graph. Right, so this is only 100 rectangles, but you can imagine if you took 1,000,000 rectangles, you would barely be able to tell the difference, right? Okay, so this is going to be the idea is to get the exact area, we're going to first understand how to approximate it with just a few rectangles, and then see what happens as we take that number of rectangles and make it very large. And that'll eventually turn out to be we're computing a limit at infinity. And so what we're going to concentrate on now is we're just going to concentrate on making sure we understand how that we can make sure we can set things up for when there's a small number of rectangles, like 5 or 6 rectangles. Because it turns out if you can understand how it works for like 5 or 6 rectangles, then you can basically understand how it works for an arbitrary number. Okay, it works the same, it's just, it's more work to compute them all, right? And at that point, you leave it to a computer. Okay, so that's where we're headed. That's our goal, is to figure out how to draw these pictures and how to actually figure out what these approximations are. And then in the next section, we'll add the piece where we send the limit off to infinity. Okay, so any questions so far? Okay, so let's get to the approximating part. Let's put the word. Okay, so yeah, that's our goal, is to approximate signed areas with rectangles. And our first question is, oh, you guys can't see this, sorry. Yeah, okay, here it is. So we want to approximate signed areas with rectangles, and the first thing we have to understand how to do is how to divide an interval up into pieces. And we're going to divide our intervals. Divide an interval. We're going to choose to divide it into n equal pieces. Yeah, of n pieces of equal size. Maybe let's not use size. Let's say length. Okay. And part of what makes this whole business difficult is the notation. And okay, so let's just dive right in. So let's imagine a number line, and then let's put our interval. So let's say we're doing the interval a to b. Wow, this sentence didn't turn out right. So we wanted to divide an interval to n pieces of equal length. And the interval we're going to do is just, it starts at some a and it ends at some b. Okay. And so if you think about it, the total length, what's the total length of the interval? It would be the distance from a to b, which just turns out to be b minus a. So that's the best way to say this. So the length of each piece after we divide it up. So if we're dividing it into n pieces, so you can imagine like dividing it into like 5 pieces. So you would take the total length, that's b minus a, and you would divide that into, say 5 pieces. Here it'll be n pieces, where n could be, whatever number you're using. And this quantity, we just give the name delta x, because it's sort of the change in x over each interval. And delta stands for changes. And so then what happens is, let's imagine that there were exactly, let's say, what is this, 5 intervals? Yeah, so if we divide, so just to illustrate, maybe n is 5, divide this into 5 pieces, then what are the endpoints of each piece? So our first piece is here, from A to here, but what's this first blue dot? So I guess technically we should put blue dots here. So this one would be A, and then you started at A, and then you move to the right by delta x, right? And so you'd go at A plus delta x. Then to get to the next one, you go another distance, delta x again, right? So you get A plus another delta x. That ends up being 2 delta x, and you keep going like that, right? Until at the end, you get A plus 5 delta x, which ends up being b. Just kind of the way the math works out. You could also write these as like A plus 1 times b minus a over n. A plus 2 times, because delta x is just b minus a over n. Right, you could write them out that way as well. Okay. So yeah, the first main thing we remember is that if we're dividing an interval into n equal pieces, the length of each piece will be b minus a over n. And if we want to find the endpoints of the interval, we can start at the left endpoint and then add delta x each time we move to the right to get all the little endpoints in the middle. Right, so we've divided up into 5 pieces here. That's the first step. So let's just do a simple, quick example, make sure we all understand. Let's divide the interval minus 2 to 5 into 8 equal length pieces. And label the endpoints of each segment. Okay. So here, the first thing you would probably do is you would just calculate, you always have to know so the total length of the interval here would be end minus beginning. So that would be the b minus a over n. And the n is 8, so we're trying to divide it into 8 pieces. So total length over number of pieces, that gives us what? 7/8. So it says the length of each segment is 7/8. Okay, and then if we draw this on a number line, over here is minus 2 somewhere. Over here will be 5. And then let's see. In the middle, so we need what, 7 dots? So there'll be a dot in the middle. Or maybe let's use dots. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay, now we're basically asking, like, what is the number at each of these blue values? And so the leftmost one is just -2. Then if I move to the right, it'll be -2 plus 7 over 8. Then if I move over again, it'll be -2 plus 7 over 8 plus another 7 over 8. So that would be 2 times 7 over 8. Right, and you can keep going like this. Yeah, and probably at this point you get the idea, right? This last one would be -2 plus 7 times 7 over 8. And then the very last one would be 5, right? Okay. So does this make sense to people? And later we're going to have another notation for this. So we're going to call the leftmost one x sub 0. Then each time we move to the right, we're going to increase the subscript. So later we're going to think of them like this. It just helps you, keep track of the endpoints in sort of a uniform way. Okay, so that's the first step, is making sure you know how to divide up the interval. Next, let's just jump right into doing some estimates. Okay, so let's do this example. Let's estimate the area under, so really we mean the signed area. Well, I guess we're doing 9 minus x squared. Let's say over the interval 1 to 3, using n equals 4 rectangles. And also, you may have to use right endpoints, because it turns out there's many ways you could draw these rectangles. And I'm going to emphasize just a few of them. I guess 4 of them. Okay, so this is the idea. So let's sort of draw a picture so we know what's going on here. So 9 minus x squared is a downward facing parabola that's shifted up by 9, so it looks something like this. And if you think about it, at 3, if you plug in x equals 3, you get 0. So here is 3, and 1 has got to be in here somewhere. Okay. And so ideally what we'd want, our ultimate goal will be to say, like, what's this area? But before we can do that, we have to kind of take an intermediate step and figure out, like, just how do we approximate things. So we're just going to do it for a small number of rectangles. So the first thing you would do is you would divide your interval up. So that means you would find delta x, which would be 3 minus 1 over the number of rectangles, which would be 4. It's 2 over 4, which is a half. Then you would divide your interval up, so you have to go up by a half each time. So this would be like, let's keep those in blue maybe. So you would have 3 halves, 2, and then 5 halves. Okay. And then let's get rid of this line. Okay, and then so the way it works is let's actually just zoom in on this. Okay, so let's zoom in a little bit. And so the idea is you look at each interval individually. So let's first look at this first interval between 1 and 3 halves. So in the problem, it said that we're supposed to use right endpoints. Okay, so what that means, I haven't said what that means yet. What that means is you look over this interval and you choose the right side of it. So the right side would be 3 halves, right? And so you follow that up to where it hits the graph, and then you draw a horizontal flat line over the interval you're working with at that value. So what we're really doing is we're saying, well, the function is just this value over that whole interval. That's our estimate. It's not a great estimate, but it's an estimate. And then you would repeat for each of the next intervals. So you might you now do this part between 3 halves and 2. Because we're doing right endpoints, you would take the right-hand side of that at 2, follow that up, and draw a horizontal line over that interval to get your rectangle. And then you keep repeating this for each interval. So here, this right endpoint would be at 5 halves. And then the final one, from 5 halves to 3, the right endpoint would be at 3. And the y value there is 0, so that rectangle actually has no height. Okay, and then what we're going to say is our estimate of our area is this area. Okay. And let's think about what these areas are. So this is a rectangle, so it'll just be width times height. So and for the first one, its width would be just a half, and its height will be whatever the y value is, right? And the y value was at 3 halves, so it'll be a half times f of 3 halves. Right, and we're multiplying these, right? And then the second one would have area. Its width is again just a half, right? 2 minus 3 halves. And so yeah, I mean, this is one part, right? These widths down here are always just delta x, which was a half for us. And so this would be a half times the height here, which is just f of whatever f of 2 is. Then this one would be a half times f of 5 halves. And this one will just be 0, but a fancy way to write 0 here is a half times f of 3, and f of 3 will be 0, right? Okay. So is this making some sense? Okay, I'm going to zoom out a little. And so what we've concluded is that our area, our approximation of it, it's definitely not exact, right? This is missing a bunch of area, right? We're missing a bunch of, we're missing all this stuff in here, right? So it's going to be too small, but it's a start. We're just trying to understand how we make these approximations. So our area would be just the add up all these green areas. So it'd be a half, or maybe let's keep it in the same color. It'd be a half times f of 3 halves, then add the next one, add the next one. So we're just adding up all the areas of all the rectangles, right? And if you work that out, it would be, you would plug it into f, so you'd have half times 9 minus 3 halves squared, because our function was 9 minus x squared, right? Half 9 minus 2 squared. Right, so you'd plug everything in, and I'll just tell you that if you did that here, you would get 8. Okay. And like I was just saying, is this an underestimate or an overestimate? So if we were to compare this to the actual exact area between 1 and 3, what do you guys think? Is it an underestimate or an overestimate? Well, let me just get a few people to answer in chat, please. Think it's an overestimate or an underestimate? Yeah, the value we got here is definitely an underestimate, right? Because the real area would include all these parts on the top, right? It's missing all this light green stuff, right? Okay, good. Sometimes it's not obvious whether it's an underestimate or an overestimate, but here it's very clear that it's an underestimate. Okay, so that's sort of the procedure, is you divide up your interval into the number of rectangles you want. Then you have to make a selection. So the selection for us will be, it could be right endpoints, it could be left endpoints, and we'll also have two other ones, upper and lower. Okay, they're all just different ways of taking the approximation. They give you a little bit different numbers, but it turns out you can use any of them to compute the exact area later. Later we'll learn how to do that. Let's see, what do we want to do next? How much time we got? Not that much time. Yeah, let's jump to one of these other examples. Okay, here's one with left endpoints. That'll be a good one. Okay, so here we have a very similar function. And now we're going to do it using 3 rectangles with left endpoints. So the way you are, so that, these left-right business, these are called, the way you're selecting samples or selections. You might see that term. Okay, so how would we approach this? So we want to estimate the area between this function over the interval -1 to 2. And so what we would do, so let's just sketch the graph. So here, this is very similar to the previous graph. It's just 1 instead of 9. So it's going to look something like this again. Something like an upside-down parabola. And if you look at it, -1 is here. And then that means 1 is here. So maybe we have to go out a little bit further to get to 2. say 2 is like here. So we might have to continue this. Whoops. Okay. And so, yeah, our interval is from, whoops, I don't want that. It's from -1 to 2. And we want to divide that into 3 pieces. So I'm actually going to erase this 1. Nope. I guess we leave that. So we would calculate our delta x, which would be 2 minus end minus beginning. So the total length over the number of rectangles, which is 3. So this would just get 3 over 3, which is 1. Okay, so that means we're actually fine leaving this here, because it would go -1, then we would go to 0 in here, then we would go to 1, and then we would go to 2. Okay, and then we would look at each interval. So in the leftmost interval, be -1 to 0. Now our sample is that we're going to take the value at the left endpoint. So the left endpoint would be at -1, and the y value at -1 is just 0. And then we draw a horizontal line over the interval we're doing at that height. Then we repeat for the next interval. So if we do between 0 and 1, we choose the leftmost part of that. That would be 0. Follow it up to the y value at that thing, and we draw a horizontal flat line over the graph at that value. Okay. And then the final interval would be, over here. And that one would again have a y value of 0. So the only area we would get here is this. So this is actually a really terrible approximation, right? But we're just trying to get the idea of how it works. And so if we were then to write our answer, then our area will be 0 plus 1 was the width here, right? The width will be delta x times the height, and the height at 1 will be the height at 0 is f of 0. The second one will be 0. And f of 0 is just 1, so this is just all 1. And this is not an actual equality. This is just an approximation. Pretty bad one at that. Okay. That makes sense to people? Let's see, which one should we do now? Okay, so do we have time to do all these? Yeah, we probably have. Yeah, we'll see how far we get. Let's just do another one. So this one's very similar. It's the same function, same interval, but now we're going to change the number of rectangles. We're going to change the sample, how we're sampling. Now we're going to sample at right endpoints. It turns out you can sample like at any point in the interval, but just to make it kind of more mechanical and methodical, we're choosing specific points in each interval. So this one would be very similar. This one I wanted to do because it has negative values. Okay, so let's... So this will be our 1 minus x squared. So we have 1 minus x squared. We're using the interval -1 to 2. So again, -1 is over here. 1 is over here, and then so 2 must be over here. let's say 2 is like over here. 2. Okay, and now we're going to split this up into 6 pieces because n was 6. So that means we got to figure out what's the length of each piece. So that'll be 2 minus -1, length of the interval over the number of rectangles. That'll be 3 over 6. That'll be a half again. So then you would move to the right by a half each time. So here you would get just minus a half. Move to the right a half, you get 0. Then this isn't quite to scale. Then we'd have 3 halves. Okay, and then you should double check, do I have the right number of intervals? I have 1, 2, 3, 4, 5, 6. You know, if this was a perfect graph, they'd all be the same width, but my graph's a little funky. Okay, and now, you know, you look at each interval. I typically move from left to right, but you could in principle start anyway. So if you'd like look at this interval, you would look at now the right side because we said right endpoints. So the right-hand side would be here. You would draw a flat line at that level. So that one has no height. Oops. Oh, sorry, we were supposed to draw that this way. You're supposed to draw it over the interval. So sorry, this one should have gone this way. Then if you were to do another interval, maybe you do this one between a half and 3 halves. Then you would follow that to the graph, and here the value is negative, but you still do the same thing. You still draw a horizontal line over the interval at that level and make a rectangle out of it. It's getting more and more crooked. Okay, and yeah, you just do this for all the intervals. So let's go back over here. The leftmost one would be -1 to a half. The right endpoint of that would be here. Then the next one, the right endpoint would be at 0. So you can follow that up, and it's in the middle. From 0 to a half. Oops, that one's a little too off. Okay, and then we missed this one at the very end. That part would be at -2. You would follow that way down here. Let's get rid of this. Let's something like that. Okay, and so the area we would get now is this. And once you've done a lot of these, you can sometimes you can skip the pictures, at least for the left and right endpoint ones. For the upper and lower, it's harder. Okay, so the area we would get here, our approximation, is that would be the delta x was a half, so the width of each of these will be a half. The height of the first one was the y value at the right endpoint, which was -1/2. And be f of 0. So it's a half f of 1 plus a half f of 3 halves plus a half f of 2. Okay, and it's always worth checking that you have the right number of rectangles, right? We wanted 6 rectangles, so this is 1, 2, 3, 4, 5, 6, because it can be easy to get a little bit too carried away and put an extra one. And then you would plug all these in, right? You know, so you'd have like a half times 1 minus a -1/2 squared. And Another thing I should mention is sometimes you get sick of writing all these a halves, right? Because a half shows up at every single one. So one common thing to do is to get rid of all the halves and just factor it out and just write it out in the front. Okay, now what do I have to fix in here? Plus f of 2. So you can just factor it out. That can save you a little bit of writing. So yeah, and then you would just throw this into your calculator and you get some number, right? We don't care right now too much about what that number is. I mean, I would like you to be able to calculate it with a calculator, but that's about it. Okay. Okay, so that you should have some idea now how to do left and right. So one comment I want to make is about our selections or samples. Okay. Okay, so if we're doing something where we have n rectangles, and what's the other piece? And the interval is a to b, then we're always going to call the leftmost endpoint, the a, just x sub 0, because we start counting from the left. And x sub n will be b, the nth point. And the way there's formulas you could memorize that'll turn out to be somewhat useful later is, so for left endpoints, so you have to go back and think about, maybe I should draw a picture along with these. Maybe that would help. So we're trying to divide our interval up and figure out which point are we selecting in each interval to draw our, to find the y value at. And so what we said we do is, you divide it up into a certain number of segments. Here, my picture only has 4. And then we kind of label these points from left to right. Okay. And it turns out in this language, the formula for the left endpoints is, well, in the first interval, the left endpoint of that would be just x sub 0. Then in the next one, it would be x sub 1. And it turns out you can write that as x sub I. So the left endpoint of the ith interval is the left endpoint of the overall interval, and then you move to the right I times. And really, we only care about when I is between 1 and n. Okay, so this is sort of an abstract way of writing the left endpoints. You can do the same thing for right endpoints. And if you're going to memorize any of these, I would say memorize the right endpoints one. That's the one we'll be using nearly all the time later. Okay, so let's... Sorry, I have these backwards. This one should be I minus 1, because the leftmost one yeah. This is why these formulas are annoying. But sorry, the one I wrote down was for right endpoints. But this one's for 1. Still, this part of it was right. Because now if you plug in, the first interval has left endpoint a plus 0. which is correct. For the right endpoints, it was just what I had up before. The right endpoint of the ith interval is a plus. Now you go one further. Instead of going I minus 1 to the right, you go I to the right. So the right endpoint of the first one would be a plus delta x. Okay, so those are the ones we've sort of seen pictures of. There's two other ones I'd like you to know for quizzes or exams. There's actually a third one that I'm going to let you sort of like figure out on your own on the homework, where you take the middle of the interval instead of the right or left, called the midpoint. But I won't test you on that one. So there's one called the upper estimate or upper sum. And then there's no formula for this. It's just choose the value that has the largest output. So you're basically looking at each interval and asking where is the output the largest. You're finding the absolute max on that interval. And you can do the same thing with the lower. And the nice thing about these is you always know that these are either an upper estimate for the upper estimate or it's an underestimate for the lower estimate. This would be choose the value that gives you the smallest output or y value. Okay, so that's sort of these are sort of the abstract definitions. We saw examples of left and right endpoint. I want to do one of upper and lower. And we don't have too much time left, so this will have to be our last one. Yeah, this is a good one. So it's the same function we've been doing, but now we're going to do an upper sum with 5 rectangles. Okay, so let's first just draw our function. Okay, so our interval is the same. It's still from -1 to 2. Let's say 2 is over here. And we want to divide this into 5 pieces still, or well, five is different, but the process is the same. So delta x will be the total length, which was 3, 2 minus -1. For n is 5, so here delta x is 3/5. This is a little bit of an awkward number, but so you can think of -1 as being -5/5. And then each time I move to the right, I'm going to be adding 3/5, so this will be -2/5. Add another 3/5, so I end up at like 1/5. Add another 3/5, so I end up over like 4/5. Remember, this place where it crosses the x-axis is 1. And then I get over here to somewhere like 7/5. And then 10/5 is 2. Okay, and now the only thing different about upper sum is where do you choose the y value. So here, I look at, so over the first interval, I figure out, where is the graph the highest? So the graph is the highest at the left endpoint. So I draw my horizontal line where the y value is highest. And so, for an upper estimate, the horizontal line should always be over the graph, over that interval. Now, in this, what's tricky is, like in this second interval, where is the graph the largest here? it's not at the left endpoint or at the right endpoint. It's actually right in the middle somewhere. So it's right in the, it's like right here. And so you draw a horizontal line at that value. Over this interval, right? And for the third interval, now the highest point is at the left side, right? So I can switch between like left, right, middle. You just have to look at each one individually and decide where is it largest and use that as your approximation. Because the reason, you might use this is if you want to make sure that you err on getting too much error. If you want to avoid ever getting too little, that you might use an upper estimate. And then on the next interval, the highest side, so you always just choose the highest. It's not the farthest away from the x-axis. It's literally the highest. So it's still on the left side. So you get this little squat rectangle. And then over the last part, you would still see where is it highest, right? It's still highest here. And so you would draw a horizontal and then make it into a rectangle. So the area you would get here is you have to add up the areas of these rectangles. And so upper and lowers are a little trickier. You actually have to look at like what's happening to the graph. You can't just blindly plug in left or right endpoints, which makes it tougher, right? So our area approximation would be, so all of these have width 3/5, and then the first one, it would be f of the right endpoint. In the second interval, it was largest at 0, which was in the middle. Then it was largest at the left endpoint, which was 1/5. Then it was largest at 4/5. And then the last one would be 7/5, f's of 7/5. So you'd have to plug all these into the function, calculate it out, and that would give you some area. Okay. All right, so we're going to have to stop there today.